over to you to introduce our speaker in our session for today. Thank you.
Okay, great. Thank you so much, Julianne. And good afternoon, everyone, and welcome to space. Today, our speaker is Dr. Sarah Ballard, who comes to us from the Department of Astronomy at UF's Bryant Space Science Center, where she's an assistant professor studying exoplanet discovery. Dr. Ballard earned her bachelor's degree in astrophysics at UC Berkeley and Ph.D. from Harvard University. She did her postdoc work at the University of Washington as a NASA Carl Sagan Fellow, and then went on to MIT as a Torres Fellow for exoplanetary science, and ultimately landed at UF, where her interest in exoplanets has grown wider as the number of known exoplanets has grown into the thousands. And I think that's in large part thanks to the Kepler mission and then TESS, or the Transiting Exoplanet Survey Satellite that was launched in 2018 to survey the brightest stars near the Earth for transiting exoplanets, which I guess has provided or will be providing prime targets for further characterization by the James Webb Space Telescope that was just recently launched. Dr. Ballard's research program centers upon statistical studies of exoplanet populations, with a particular focus on planetary systems orbiting small stars. She aims to answer whether there exists a typical planetary system around these types of stars, and whether that blueprint is amenable to the evolution of life. So to that end, she has led studies and advised students to address the diversity of planetary systems orbiting M-dwarfs, links between late-stage planet formation, and the observed yield of the Kepler and TESS missions that have detected orbiting nearby small stars. Also on what timescales these planetary systems are dynamically stable, and whether these planets typically host large extended atmospheres. She's also involved in the Minerva Australis project, an observatory in Australia built to gather both radial velocity and photometric observations of new exoplanet systems. So with that, I'd like to welcome Dr. Ballard, whose talk today is The Last Generation of Lonely Astronomers. Welcome, Dr. Ballard.
Thank you, Paula, for that lovely introduction. It's my pleasure to be here today virtually with you all. I wish it could be in person because these are some of my favorite things to do, giving talks to members of the public. And I want to encourage you to ask questions during the talk. If you do have a question, I truly would not mind if you ask it during the talk, either by raising your hand or honestly by speaking up. I will do my best to make sure that if you raise your hand physically, I'll have trouble seeing because I'm about to share my screen. But I do encourage questions at any stage. It would absolutely be my pleasure. Let me share my PowerPoint with you. So I titled my talk, as Paula introduced a moment ago, The Last Generation of Lonely Astronomers. And the reason why I selected that title, the reason why I've selected that title for public talks in the past 5 years or so, is because of a pathway that we're on as humanity, right? Like as a species, as far as situating ourselves in the place of living things in our own Milky Way galaxy. So in particular, Paula mentioned that I was a Carl Sagan Fellow. Often students that I teach now won't have heard of Carl Sagan, but he's really a mentor of mine. And he's someone who tried to contextualize not only space, but like human beings' place within it. And in particular, if we're trying to understand how life came about on planet Earth, one of the best ways for understanding oneself in almost any situation is trying to put oneself in context. And that's also true for our own planet, and it's true for life on our own planet. So thinking about astronomers is to think about human beings looking out, and whether or not there are creatures on other planets who are looking back at us, I think is something that will be addressed on a shorter time scale rather than longer. And I want to describe why that's so of this particular period of time. So I have this starting slide that shows, like on Google Maps, how do we get to the nearest alien Earth-like planet? But in my opinion, any talk about planets orbiting other stars has to start at home. We have to put our own solar system in context and also attempt to understand what it is about our solar system in particular, which was amenable to the evolution of life, at least on one of the solar system worlds and potentially on more than one. And so what I've opened with here is a movie from NASA's Solar Dynamics Observatory. This was a movie that was gathered in 2012. And you can see here that there's various moving pieces happening. One of them is that you are seeing the movement of the planet Venus across the face of our home sun. So you can see probably my cursor here showing Venus. Venus doesn't actually move this fast. This video was actually taken over a period of about 10 hours. And yet, even in this period of 10 hours, you can also see a hint of our own star rotating over that time. And also you're getting a hint for how dynamic the surface of our home star is. And yet, even if all of this beautiful resolution was reduced to a single pixel, right? So even if all of this picture was reduced to one single point of light, removed infinitely far away, we could still infer the presence of Venus remotely. So even if we weren't able to resolve other stars in the way that we can resolve our own home star, the idea here is that if a planet goes in front of its star, it's detectable by virtue of the planet blocking some of the starlight. So even if we weren't able to see all of this resolution, to see the hint of the star turning and its like roiling, boiling surface, by virtue of the fact that planets block a little bit of light when they go in front of their stars, we could still know that Venus was there, even effectively infinitely far away. This method of finding planets is called the quote unquote transit method. What I'm showing here in this animation from the European Space Observatory is this scenario up top, which again, we can't see from infinitely far away. We can only see for our own very own star. And what you can see is, I thought two axes would appear here showing as a function of time. Oh, there they appear. As a function of time here, what we actually observe is the brightness of the star, right? So this quote unquote transit signature encodes information not only about the presence, the mere presence of the planet, right? So when you look at another star and you see this telltale transit signal, you not only know that the planet is there, you can also infer information about its size based on how much of the starlight is blocked. And on top of that, you can determine where the planet is in its orbit around the star by how often this transit signal repeats. This is only one way that we know of to find planets, and it did not used to be the way that we had found the most exoplanets, but it is today. In order to give a sense for the importance of a particular mission, a particular NASA mission that changed fundamentally our understanding of planets, I want to walk through what the journey was like up until that point. This was an animation that was produced by a professor who's now at Princeton. And what I'm going to be showing here is as a function of the mass of the planet, so I'm showing Jupiter in units of Jupiter masses here, and as a function of the size of the planet, what planets have been detected around other stars. So in particular, here's where 3 solar system planets would live on this plot. This is showing Earth. So in units of Jupiter radii and Jupiter masses, Earth is down here in this left-hand corner. Neptune is sort of midway up, and Jupiter here is residing at 1 Jupiter mass, 1 Jupiter radius. So I also want you to note this date in the bottom right-hand corner. This date is showing the sum total of humanity's knowledge about planets in this mass and radius range. So prior to 1999, the only knowledge that we had about how planets in nature occur, how nature makes planets, were solar system planets. These 4 dots correspond to like solar system worlds. I'm now going to play a piece of sound for you to hear, where you can hear the planet, when it gets discovered, make a tone noise. And that tone, the depth of tone, the pitch, is telling you the mass of the planet, and the frequency with which you hear the tone is telling you how quickly that planet moves around its star. So when you start hearing one tone, you'll know, okay, humanity has just discovered our first exoplanet around another star, starting in 1999. All right, let's can you all hopefully hear a little bit of that? So here we are in 2001, there's still only one. 2002. I want you to pay close attention to something that happens in 2009. So far the things that we're finding are mostly like Jupiter, similar to Jupiter. Once 2009 came around, the planets started increasing very quickly. This particular movie stopped updating in 2012. 10 years later, there's roughly 100 times as many planets as you can see here populating this diagram. But I like using that sound experience to convey not only the fact that we're finding these new planets, but the fact that they are so common. So why was it that we didn't see them until now? All of that changed because of a particular NASA mission. So let me describe the type of change that happened. I've shown it in that figure and you can sort of hear with sound how it happened. Now let me describe it in terms of the planets themselves. This is basically in 2008, half of the planets that had been detected using the transit method. Right, so like as of 2008, I was just starting my second year at Harvard University as a PhD student. There was roughly 50 planets that had been detected using the transit method. This is showing half of them. And what you can see with these like pink bubblegum looking circles are the relative sizes of stars, right? So a sun-like star would be roughly this big in this context. So you can see that we are finding planets around stars of a variety of masses, but mostly similar in size to the sun, with the exception of this one down here, orbiting a small star. What you can see with the relative dot size is the size that we think the planet's silhouette is against the star. What we actually measure is this thing on the bottom, which is showing the shape of the brightness of the star change as the planet goes in front of the star. Yet, these are all planets, which are roughly comparable in size to Jupiter. So this is the relative size of Jupiter casting a shadow on the sun. So what we were sensitive to in 2008, largely Jupiter-sized planets going in front of sun-like stars. That was almost all that we had seen until NASA's Kepler mission. Now I'll describe the way that the mission looked for stars. It was using the transit method, and it affixed its gaze to a part of the sky, which is overhead at about midnight in the middle of summer in Gainesville. And the patch of sky that it looked at is roughly the size of your outstretched hand held at the end of your arm. So within that patch of sky are hundreds of thousands of stars. And Kepler, this is what Kepler saw in a single exposure, was monitoring every single one of these hundreds of thousands of stars, looking for this telltale dimming signature. So think of Earth, for example. If we were asking how often does Earth produce a transit signal? Well, it would produce it, if for an alien observer, every time Earth completed an orbit. That means if we were looking at an exact Earth analog, we should see one transit appear every year. And if you happen to look away, right? If you happen to flinch in that moment, you would completely miss the transit altogether. That means that any kind of transit mission, which is designed to see things which are further away from their stars than even a few days, requires a mission in space for which there is no day and night issue. You can simply stare, which is why this mission had to go into space and couldn't happen on the surface of Earth. It stared at a particular part of the sky and basically didn't blink for a period of 4 years. This is the sum total of the knowledge that we had about planets in this part of the sky prior to the launch of Kepler. This is one of the 23 planets that were on the previous slides. And And as of 2013, these are the locations of planets that Kepler had found. Dennis Overby, who's a science writer for the New York Times, referred to this as the Skittles diagram. And the Skittles here are showing not only the location of stars that we think have planets, these dots are showing you information about the relative size of planets. So let's think about the previous slide for a moment, right? Where I was showing that family portrait with a couple dozen planets, all Jupiter-sized. Yet Jupiter-sized planets, giant-sized things, Jupiter is about 10 Earths across. So that would be red dots would be Jupiter. Looking at this plot, even though all we had found was Jupiters, prior to the launch of Kepler, Jupiters are actually not the most common type of planet. Rather, the most common type of planet is in between Earth and Neptune, approximately. So my colleague, Leslie Rogers, she's a professor at the University of Chicago. She likes to talk about planets that are intermediate in size between Earth, the largest of the terrestrial worlds, and Neptune, which is the smallest of the gas giant planets. In the solar system, there is no world in between those places. We have only rocky planets as large as Earth and gas giant planets as small as Neptune. We have nothing in the middle. These are 0% of the planets in the solar system in this intermediate range, yet we think they are 80% of the planets in the Milky Way. Are planets which are in between size between the Earth and Neptune. And so why weren't we detecting them before? It's because Jupiter-sized planets are just the lowest of the low-hanging fruit. The things which we were sensitive to from the ground had a proportionally large signal and were amenable to observation from the ground without having to go into space. So the fact that all we had found was Jupiter-sized planets before wasn't a reflection of the fact that there were only Jupiter-sized planets to be found. All of these delicious planets, Earth and super Earth sized planets were just out of our reach from what was possible from a ground-based platform. And the space-based platform has enabled this complete revolution in our understanding, not only of how common planets are, but also the diversity of their types of planets. I'm just going to pause for a second in case there are questions about this so far. I'll continue in a moment if there aren't any. Yes, Paula, and I see, is Richard speaking?
Yes.
Yeah.
I guess the concern I have is between the gas planets and the hard rock planets.
Yes.
Or apparently, because you've chosen to use Jupiter as the index
Yes.
of size, and it's a gas giant.
Yes.
The hard rock planets are all down in the lower scale. Is that correct?
Yes.
Why is that?
The answer for that has to do with the history of how planets form. It's sort of an hourglass trade-off in how we believe planets form. They form, we think, from a primordial cloud of gas and dust. If you collect enough rock together that your gravity is strong enough to hang on to the hydrogen, which is present in the disk, before the sun turns on and blows the hydrogen away from this like forming planetary system, then you have a chance at becoming a giant planet. So the question, it's really like an hourglass question. Do you get big enough, fast enough to hang on to the type of hydrogen helium atmosphere that makes Jupiter a quote unquote gas giant? So if the rocky planets were bigger, it stands to reason that we would have resembled Jupiter more. So it's really a question, are you strong enough during formation? Have you collected enough mass together quickly enough to hang on to that hydrogen and helium? That's really the trade-off. So the reason why we haven't found things which are rocky in nature and not gas giants in nature that are much bigger is because things that are that big tend to grab very thick hydrogen helium atmospheres, and Earth was not massive enough to do that.
Thank you.
Yeah, sure. Did you have a question, Paula, or were you just pointing out?
Well, I do, but I'm thinking I might hold it till the end. I don't want to rob you of your time to get through your talk, because we're a questioning bunch. So
Okay, I'll just
easily eat up your time. So I'll hold till the end.
Okay, so now I'm showing an updated version of this census picture. Okay, so previously, right, here's 23 of the 50 known. Now here are a sample of the thousands and thousands which are known. And let's just zoom in on a part of this sample. So what you can see is just like that previous figure, you're seeing the relative size of stars, and in front of them, a shadow of their planet, or what we think is the relative size of this planet. So Jupiter transiting the sun would lie about 2/3 of the way up this diagram, right? So that means that actually the vast majority of stars which Kepler found planets around are smaller than the sun, right? So in this ordering of host stars here, if we're 2/3 of the way up, look at how so many of the stars that we detected planets around are actually much smaller than the sun. This was one way in which this mission really surprised us. I'm going to walk through this figure, which came from the literature. So this is the single most exciting figure in astrophysics that I came across between 2010 and 2020. And let me describe why it's so exciting. This is showing as a function of the temperature of the star, right? So nature makes stars across a variety of temperatures. Some stars are hotter, some stars are cooler. Cooler stars would be down here on this axis, hotter stars would be up here. The y-axis is showing the number of planets per star, right? So this is showing what we were sensitive to. Look at the colors here. The colors of these bars are showing planets of different sizes. So let's orient to what we were sensitive to prior to Kepler. If we're looking at Jupiter-sized planets, well, that's 10 times the radius of the Earth, right? So we're looking at this blue line right here for Jupiter's, for example. The sun is right here in this scale. It's at about 5,800 degrees. And if you look at the number of Jupiter-sized planets per sun-like star, sure enough, you see that there's about 0.01 per sun-like star, which means like roughly 1 in 100 sun-like stars host a Jupiter-like planet. But that is not where the majority of planets are, right? Actually, what you're seeing is that way more common, way more planets per star are intermediate in size between Earth at 1 Earth radii and Neptune at 4 Earth radii. But even more intriguing than that is that that number seems to increase as the star gets cooler, as the star gets smaller. And the reason why that's so compelling is because this really is very advantageous for those of us that are hoping that there's life elsewhere in the Milky Way. That's because not only are small planets, potentially terrestrial in nature, more common around small stars, these small stars themselves are the majority of stars in the Milky Way. So small stars, half the mass of the sun and smaller, are about 70 or 80% of the stars in the Milky Way, yet they are 0% of the stars you can see with your naked eye. So if you could see these small stars, right, if you had eyes which had evolved not to be sensitive to the light of our own home star, our eyes evolved to be sensitive mostly to the light of our own home star, but rather could sense red and even infrared light better, what you would see in the night sky is roughly 7 or 8 stars appear for every star that you can see with your naked eye. You would see the galaxy's multitude of small stars. That's why if you were a person who was incredibly interested in planets orbiting stars, this would be such good news, because not only are small planets common around small stars are themselves the majority of stars in the Milky Way. That probably means that our Milky Way is teeming with planets, the vast majority of which are orbiting stars which are not like the sun. And to bring this point home, what I'm showing here is the stars off of our back porch. So this is showing a 3D map of stars which are within about 100 light years of Earth. Namely, so thinking about when I Love Lucy started airing, like in the 1950s, that means that those broadcasts on Earth have had about 50 years to be transmitted. So if a transmission of, or 70, closer to 70 years. So if a transmission of an I Love Lucy episode that aired in 1955 left the surface of Earth, it would not have even made it to these stars, which are at the outskirts here. That signal would only have reached about halfway out here, right? So like this question of how far things are away is a question which is difficult for us to conceive of in units other than time, right? So this is showing within 100 light years, the number of stars we have, stars that are off of our back porch. And you can see that the vast majority of them are colored red. That's because this is color coded based on the type of star. So-called quote unquote M dwarfs, which are those stars which are half the size of the sun and smaller, the ones that would have appeared here, showing in red. The ones that are the vast majority of stars in our galaxy are depicted in red here. Stars that are like the sun are shown in yellow. So what we learned from Kepler is how common these small planets are around small stars. It stands to reason that the patch of the sky we looked at from Kepler is not unusual in any way, right? So like the stars that we observed from Kepler, Milky Way stars, those can't be special for some reason by virtue of the direction that they're in. It must be that stars in that part of the sky host planets in the same way as stars which are nearby us. There's no reason why they should be different. So taking the statistics that we learned about from Kepler for how common planets are, and in particular, how common planets are around small stars, we can take that statistic and figure out how many Earth-sized planets must be relatively off of our back porch. I'm showing here a quote from 2013. Oh, pardon. This young woman was a graduate student at the time that she made this quote. So from Kepler, she said, with 95% confidence, from what we learned from Kepler, there's an Earth-sized planet in the habitable zone of a small star. And by habitable zone, she means orbiting at the right distance from its host star, that water would be in its liquid form, as opposed to its steam form or its gas form. She was making a prediction based on Kepler. This young woman is now a professor at UC Berkeley. So 10 years have passed. And sure enough, we found this planet. So this particular planetary system was discovered a couple of years after the fact. It is around one of these stars, sure enough. So it stood to reason what we learned from Kepler must apply to the stars that are off of our back porch. And indeed, what we discovered is among the nearest stars, there is a host star. Of course, it's a small star, right? Because we know these are most common and they most commonly host small planets. An additional planet has since been discovered since this beautiful graphic was made. So this is a small star which hosts 8 planets, which are close to being Earth-like in their size. We think probably Earth-like in their composition. And what you can see here with this graphic is showing the relative state of water that we think is most likely for these planets given their distance from their home star, so that water on these Earth-sized worlds, which are closest to the star, is going to be steam, and water in the worlds which are furthest away is going to be in its ice form. Yet there's several planets here, more than one, orbiting a single star, which are Earth-size and potentially Earth-like. And on top of that, if there is water on those worlds, it would probably be in its liquid form. This really changes the nature of conversations about the potential for life on other planets. To return to Carl Sagan, he posited that perhaps there could be sentient octopi in the atmosphere of Jupiter, right? Like to think about life on other worlds is to try to expand your imagination. But most scientists, including Sagan, thought that in order to evolve life, you probably need a murky puddle to start. You need 2 things in order to have a murky puddle in which molecules are free to bump into one another and potentially make the building blocks of life. You need to have a terrestrial surface, right? The way to see a puddle is to have a rocky surface that can support a liquid of some kind, and then to have that material be in its liquid form. And I want to describe a really important point that follows from this argument that I've just made. So not only are planets common, small planets are common. Namely planets that might have rocky surfaces, right? And that might even have liquid water on their surfaces, yet they're most common around small stars. This is a point at which I hope I've conveyed enough motivation to say that we are not usual by virtue of the fact that most planetary systems aren't around sun-like stars. That means that by virtue of that fact alone, we are not a typical planet in the Milky Way. Earth is not a typical planet in the Milky Way because we are orbiting a star that's too big to be typical. And that means changing our thinking about what is typical. I just want to highlight one particular feature here. So this is showing like, as a function of the mass of the star, how far away from the star you need to be in order to reside in this nice, perfectly warm, not too cool, not too hot yellow stripe. So here's the solar system around a G-type star, which is 1 times the mass of the sun. So we're right here orbiting the third planet from our sun. And sure enough, we around our own star are just the right distance, right? To reside in this yellow swath, to be the right temperature to have liquid water. Yet these small stars glow much more dimly. Just like having to huddle more closely around a campfire that's burning down, you would have to be a planet huddling much closer to a small star in order to be warm enough to have liquid water. And crucially, that lies inside this dotted line right here. It would be easy to miss, yet it literally is the difference between night and day. This quote unquote tidal lock radius corresponds to the distance from the star at which you would cease to have night and day. You would be close enough to your home star that interactions due to tides would produce a situation that we are experiencing with our moon. For example, where the same side of the moon is always facing the same side of the Earth. The other side of the moon is not visible to creatures on Earth and wasn't seen by human beings until we left the surface of our planet. So that type of scenario happens because of tidal interactions. When things get too close to one another, we think it probably happens around every single planet orbiting a small star in its habitable zone. And in order to convey what that might mean, sometimes I actually have to turn to art. I was giving a lecture just last week in the art department here at UF with a graduate student of mine who is also an artist. That class was about artistically conceptualizing immensity, conceptualizing the immense. And she and I were giving a talk about how we do that as astronomers. Sometimes you use equations. In fact, you need to use equations to describe immense things. But there is a point at which equations are insufficient or they become less helpful in conveying reality, right? And human beings know this from day-to-day experience, that sometimes you are able to appreciate reality better, seeing it filtered through a piece of art. And the piece of art that I most like to convey this particular idea about what a typical planet would be like, right, is from a book called Einstein's Dreams. I'm not sure if any of you have ever seen or read this book. Hold on, I'm looking up just a piece of it right now to be able to read it to you. Okay. So in Einstein's Dreams, this fictionalized version, the author Alan Lightman is imagining Einstein attempting to grapple with ideas of time passing differently. So let's now put ourselves on the surface of a typical planet that has a liquid ocean in the Milky Way. I've argued that this is not a planet around a sun-like star. This is a planet around a small star. And being close enough to the small star where water would be liquid means that you would maybe have 1 day per year. You certainly wouldn't have 365 days per year. 1 day per year. What that would mean is that if creatures lived 1 quote unquote year on their planet, you would experience 1 day and 1 night over the course of your entire life. And that's what this particular fictionalized journal entry conveys. So I'll read it to you here. Imagine a world in which people live just 1 day. Either the rate of heartbeats and breathing is speeded up so that an entire lifetime is compressed to the space of 1 turn of the Earth on its axis, or the rotation of the Earth is slowed to such a low gear that one complete revolution occupies a whole human lifetime. Either interpretation is valid. In either case, a man or woman sees one sunrise and one sunset. In this world, no one lives to witness the change of the seasons. A person born in December in any European country never sees the hyacinth, the lily, the aster, the cyclamen, never sees the leaves of the maple turn red and gold, never hears the crickets or the warblers. A person born in December lives his life cold. Likewise, a person born in July never feels a snowflake on her cheek, never sees the crystal in a frozen lake, never hears the squeak of boots on fresh snow. A person born in July lives her life warm. The variety of seasons is learned about in books. And part of the reason why I like using that piece of art to convey this idea is because this could be the default for creatures in the Milky Way. They would have no conception of day and night. Day and night would be as alien to them as this idea that we have of a lifetime taking just one day. And yet this is probably very common. So these complications from living around a small star, I'm calling them complications, but then I'm a creature that evolved to be very comfortable on an Earth-like planet around a sun-like star. These considerations come to the forefront because we're not talking about rare planets. We're talking about the most common type of planet. So this idea, tidal locking or quote unquote spin synchronization, is something that we think is extremely common for planets in the habitable zone of small stars. Day and night doesn't exist anymore. What that means is its potential for evolving life. It's not zero, but it is possible that life would evolve under a sun that never sets. Right? Potentially life could evolve in a place where there's permanent sunrise or permanent sunset, right? Where the light might not be too intense, or the side that is cold, right? Where there would be like absolutely no sunlight that you ever would see. So this is a complication which has now come to the forefront of considerations about exoplanets because of how common these are. It also is the case that tides are going to play an important role, not just with dictating day and night, but also in terms of heating due to tides. Io, which is the nearest moon of Jupiter, is being stretched and squeezed by its proximity to Jupiter and Jupiter's tides so much that the surface is constantly being repaved by volcanic activity. So Io has volcanoes constantly going off because of the tidal stretching and squeezing, which makes it so that the mantle of Io is always liquid. That's something which could potentially be disastrous. On the other hand, we think that a little bit of heating in the core of a planet is necessary to sustain plate tectonics, which we think has been important to the long-term presence of life on Earth. So there's an argument to be made that this is simply another force of nature, that tides is simply another force of nature which has to lie in a particular range. And what I'm showing here is that as a function of distance from the star, this is showing how eccentric a planet could be, namely, like, does its orbit have to be perfectly circular, which would be at 0 here? Or could the orbit be more flattened and elongated? And what this figure is showing is that a certain distance from the star would be shown in this gray area here, is a good estimate for the quote unquote habitable zone. You would have to be a certain distance from the star in order for water to be liquid. Yet, there are entire parts of this, distances from the star, where if you didn't have a perfectly circular orbit, you would get enough heating by this tidal type stretching and squeezing that you couldn't sustain a water ocean. It would boil away from that kind of heat injection from tides. So that means that all of a sudden, things which aren't that big of a deal to creatures on Earth, like maybe a modest orbital eccentricity, something where your orbit isn't perfectly circular, could render a small planet orbiting a small star completely uninhabitable. And in addition, these small stars are also incredibly active. The type of quote unquote activity around sun-like stars that I'm referring to all happened extremely early on in the life of our own sun. Sun-like stars aren't active forever. And by active, I mean like really powerful stellar flares, producing a ton of X-rays. Yet these are happening more or less continuously for billions of years for planets orbiting small stars. Yet what's dangerous to an Earth-like organism might be perfectly comfortable to a creature that evolved on another type of world altogether. So I'm going to transition in the few minutes I have left to how I think things are going to look in terms of the actual remote detection of life. So I've made an argument in this talk about how common we think planets are, but having a planet, and even a rocky planet, is not the same thing as having an inhabited planet. So I want to walk through how this is going to look, and it uses the exact same reasoning of finding planets using the transit method. So I'm showing here, this is a real picture of a world in our solar system. Namely, this is Saturn's moon Titan, the only other place in the solar system that has a liquid ocean of any kind that's not Earth. Titan is very far away, orbiting Saturn. That means this ocean is not liquid water. Titan doesn't have liquid water oceans. Water on Titan is in its ice form. Rather, Titan has oceans, but of liquid methane and ethane. The Cassini mission that flew by Titan arranged itself in a particular way so that Titan's atmosphere was backlit by the sun. And this enables a really cool type of investigation, which we can conduct with planets orbiting other stars. Namely, we can backlight them. We can't control it like with Cassini, where we would get in exactly the right orbit, but for some set of planets, we are lucky enough to see them transit. What this mission did, it was looking at the size of the shadow that Titan's atmosphere cast when backlit by the sun. So if you had a planet made completely of rock, what you would see when backlit is the silhouette of the rock. But there are certain properties of gases where, like, we look outside, for example, in the air that we have made of mostly nitrogen and oxygen allows sunlight to pass right through, right? When we look up, we actually see sunlight. So therefore, atmospheres don't behave that way. Some types of light they allow to pass through, while others would get stopped. And that line of reasoning means that the relative size of the planet's silhouette when it transits depends on the wavelength of light or color that you're looking at. So that means the size of this quote unquote transit signal can vary, and it varies in a very predictable way. So for example, looking at a wavelength where the atmosphere is transparent, you would look at the transit and it would have a certain depth. If you then looked at that exact same planet at a wavelength where the planet was opaque, the silhouette would appear larger. And I'm going to show you what that looked like when we did this exact experiment with Titan. So this is showing Titan itself. You can just see the core, or you can see the atmosphere also included in that silhouette. This is showing as a function of color, shown along the x-axis here. How large does Titan appear? First, let's look at a wavelength where it's transparent, and then at a wavelength where the atmosphere is opaque. If the size of Titan appears to change, right, so that it blocks less light when the atmosphere is transparent and more light where the atmosphere is opaque, we can then make a map of Titan's apparent size as a function of color, which is what these authors did to conclude that there is a very particular fingerprint to the colors of light that Titan's atmosphere absorbs or allows to pass through unimpeded. We know what molecules do that and how. And in this particular case, we're able to show this is because of methane, right? That this particular feature exists. Using this exact same reasoning with backlighting an exoplanet by its own host star, you can extract information about what's in that planet's atmosphere. And the reason why I made a comment to the media when this paper came out, because I found it so incredibly exciting, because unlike exoplanets, Titan is a place we can actually go and have gone, so that the information that we would refer remotely from a study like this using this backlighting trick, we can confirm by a probe that actually went, right? So like when Cassini flew by Titan, it released a probe called Huygens. And we know from the particulates that Huygens tasted as it plummeted to the surface of Titan, the atmospheric content of Titan. And sure enough, we can confirm that it is an exact match with what we would guess from this remote technique. What I tried to convey, the reason why I found this so exciting is because this is an experiment where we can show it really works. This backlight technique to actually measure what atmospheres are made of. We run a test on it on our very own solar system, and it worked for this moon of Saturn. So that's the path forward. I think maybe I'll stop there for now, Paula, so that there's time for questions.
Okay, very good. That was fabulous. You did a great job distilling that down for us. Just fascinating. I guess I could ask the first question. So I think you mentioned early on in your talk that that we have just discovered a huge number of these smaller planets, and I think you mentioned if we could see in infrared. And I think what I remember from our talk on the James Webb Space Telescope, that's exactly what the advantage is going to be there. So is that some of the data that's coming in from that, or is this data prior to, this must be data prior to the James Webb, so.
It is.
So was it TESS that was able to see all of that, or how did we find all of those?
So the distinction that's key here for James Webb versus TESS versus what was feasible before is whether you're talking about the planet or the star. So in particular, when I was showing how there were like 7 or 8 of these red objects that appeared for every object we could see, what I was referring to was the star. And star discoveries have been happening as long as there were infrared cameras on Earth. So that goes back like hundreds or more, right? So just because we can't see something with our naked eye, we've been making progress on problems like that as human beings for hundreds of years. Either you have telescopes, right, or microscopes, or other ways of detecting things. So we've known these stars are there for a long time. The question that TESS answered and that Kepler answered is whether there's planets around them. Now, the question of James Webb and why James Webb would be specially designed to have sensitivity in the infrared is partially because of the motivation, the very strong motivation to understand planets orbiting these stars that emit a lot of infrared light. And also because so many of the molecular fingerprints that I was just describing, like the plot that I just described with the atmosphere of Titan, that was in the infrared. Because so many of the fingerprints for the molecules that we are most interested in, oxygen, right, methane, CO2, things that life interacts with, have their fingerprints in the infrared. So that's another reason why James Webb would have planned to be sensitive in that wavelength range to be most useful.
Mm-hmm. Okay, and then if I might, just one follow-up question there, then when you're looking at transiting,
Mm-hmm.
you know, it's sort of astounding that when you're looking at something as bright and massive as, say, our star, you know,
Yes.
our sun,
Yeah.
But you're a zillion, you know, light
Yeah.
years away.
Yeah.
What are we using to, like, what's the resolution of what we're using to detect the transiting
Yes.
process? And that has to be a very tiny diminution of
Yes.
how much the star is putting out, you know?
Yeah, exactly. So the first transiting planet, I'll tell you, was discovered with a very small telescope in a parking lot in Colorado, right? So a Jupiter-sized planet going in front of a sun-like star causes about 1% of the light to vanish.
Wow.
So that produces a signal which is 1%. A human eye can't quite detect a change in 1%. We're sensitive at the level of like 10%, right? Like you could easily tell if I had a dimmer switch and put the brightness of a room from 100% to 99%, a human eye couldn't really tell. But at the 10% level, you can start to tell. An Earth-sized planet, in contrast, blocks much less light by virtue of the fact that it's a much smaller planet. There you're talking about tens of parts per billion, or roughly a part in 100,000 would disappear. That requires an extremely fine ability to measure brightness. So like, it's not a question of resolving the star itself. The star can still be a pinpoint of light. All you're keeping track of is the amount of light that's coming from that star, and you have to be sensitive at the level of when 1 part per 100,000 or 1 part per million, let's say, like becomes disappears, you would be sensitive to that. And that is why that took a very long time to develop that technology.
Yep. Okay, thank you. We have a few hands up. So first hand I see is Bob Bernstein. Go ahead, Bob.
I wanted to ask whether the possibility of life on planets is an all or nothing kind of thing. let's say a planet is tidally locked, and one side is dark and cold, and one side is hot
Yes.
and bright. At the edges, at the dawn and dusk sides, is there a zone in there then that is perhaps suitable for liquid water and life?
When I think about questions like yours, and thank you for your question, Bob. When I think about questions like that, I honestly return to planet Earth, right? So is there evidence on Earth, right, for organisms that make a living in really extreme environments? Now, I'm not talking about necessarily complex organisms like mammals. I'm talking about bacteria. So there are creatures on planet Earth that never see a single particle of sunlight, right? Namely, that evolved like on the ocean floor, right? Living next to hydrothermal vents. There are also creatures, bacteria, that live under rocks in the Atacama Desert, a high altitude desert in Chile, where it rains once every 10 years, right? So the ability of organisms, the ability of bacteria especially to find a way to eke out a living, I would contend that I would bet on the bacteria. Now, I'm not talking about more complex organisms. So whether or not the temperate nature of the terminator, the quote unquote terminator, where there's like permanent day and permanent night, would extend very far, depends a lot on the properties of the atmosphere, and in particular on something we're all familiar with, which is wind speed, right? So like if you had a planet where the wind speed was relatively high, then you could take warm material, warmed from the sun on the day side, and move it around to the night side so that you would have the type of humid evenings, right, that we experience here in Florida, right? And plenty of creatures eke out a living that way. So like that, it depends not only on the planet's properties, but the specific properties of its atmosphere and winds, like how far away you could survive from like permanent day, permanent night, or even honestly, whether you could evolve under a star that never sets, right? That could be possible. And there are creatures that do that.
Okay, thank you. And that's awesome that you mentioned extreme life, because it's almost like you were a plant, because my course for next fall is going to be life in the extreme. And that's what we're hoping to be talking about.
Yes.
So Ken, you have your hands up?
Yeah, a question. I'm not sure that I heard you correctly, but it sounded like a planet that's in a orbiting a mini star, if you will,
Yes.
is in a range where the surface may be exposed to a lot of radiation, a lot more than we have. So the question is, since radiation to a large extent is deleterious,
Yes.
especially for life with the molecular biology that we understand, is what kind of assumptions do we have to make to assume that if we're going to find something that we would label life, that it would be anything that we would recognize as life, since its chemistry might have to be very different.
Yeah. I was thinking of the variety of ideas that your question brings up. Because there's the question of, if you saw life, how would you recognize it first? Like, which requires us to define what life is as a process. So there's that question, which merits its own talk. And then there's this question of, as you put it, the deleterious effects of radiation on organisms. So for example, and I'll turn again to planet Earth, which is how I always orient myself with trying to think about other planets, which is that a single UV photon, like there's a reason why we wear sunscreen, namely, which is that radiation from our own star in the ultraviolet range can be harmful to our cells. A UV photon, particle of UV light, is sensitive enough to break apart a DNA molecule. So then how did we manage to evolve? Partially, it's because bacteria paved the way for us, right? So the fact of the hole in the ozone layer, which I haven't heard about described in a really long time, but I remember it was once like a huge issue, is because of ozone. Ozone is 3 oxygen molecules put together. right? So in order to have this protective barrier, how did that come about, right? So that creatures on the surface of Earth have this quote unquote ozone layer to protect us from ultraviolet radiation, that didn't come from nowhere. Oxygen is required to make that. And the thing that produced all of that oxygen is a process that we know about well, which is the process by which plants take carbon dioxide and turn it into oxygen, right? So mammals do the opposite. We breathe in oxygen and exhale carbon dioxide, but plants are the other way around, right? Take carbon dioxide and produce oxygen. In this sense, it was very early plant life, if you could even call it plant life. It's more like primal slime goop that we walk by all the time in Florida and don't really thank for our existence on planet Earth. But part of the reason why Earth itself is habitable is because of living things that came earlier, right? That took a lot of the carbon dioxide, which was originally in our atmosphere, breathed it in and exhaled oxygen, which eventually produced this protective ozone layer. The reason why I'm bringing that up is because life, to make the point that life is not an either or process. Rather, it took living things to make Earth safer for other living things. So like that process could also be many steps, where you would have early organisms, which could be more robust to radiation, followed by later organisms, which might be more delicate, but they would have the benefit of that intervening stage where maybe the atmosphere built up molecules which would be protective against that radiation, because that's what happened on planet Earth. But to speak more broadly to that question of how would we recognize it if we saw it? So it would be presumably organisms that would evolve to be much more robust to radiation. But then we have creatures like that, like cockroaches, on Earth that have figured out a way to be pretty robust to radiation, which is you just divide your cells less often. So presumably, even if you had life which resembled Earth life in some way, there are ways that you can tune the knobs to make it more capable of surviving. But I wish there were time to get into, and and I can stay a little bit extra, but I want to address everybody's questions about how you would know it if you saw it, because that involves like, well, what does it mean to be alive? And how would you recognize something as being alive versus not alive? And that it's a scientific question, but it's also philosophical, because it would require us, for example, to determine why fire isn't alive. Right. So when we're talking about things, well, what do living things do? Well, they make more of themselves. They extract energy from their environment and make more of themselves. And fire does that. Right. So getting to the point where you could make an argument, and yet we know that fire is not alive. So you would have to make an argument about, well, what do living things do? And then whatever this process is would need to do those things. Even if it didn't do them in the same way as Earth life, if it did them, we could recognize it as a process that we call alive. But I appreciate also the complexity of that question. Hopefully I took a crack at just like the edges of it.
Yeah, Bob Bernstein was just holding up a book. It's called Life's Edge from Carl Zimmer.
Oh yeah.
A search for what it means to be alive. So
yes.
that might be a good read.
Yeah, exactly. I hope it touches on similar ideas, because it is not simple. Like you're put like, and Carl's such a great science writer. So to have an entire book considering the contours of this question, it shows how complex it is.
Go ahead, Richard.
Okay, thank you. I'd like to see if I have summarized some of your elements correctly in your talk. And I guess just fixating upon the size of the planet relative to Jupiter,
yeah,
has separated that hard rock planets rather than gas giants, or were in a lower spectrum, but there are more of them.
Yeah.
And therefore, if we were to shift our focus from measuring stars and their relationships to the planets that circle them, and then search for a second planet, because let's say Russia turns nuclear, and basically we have to go somewhere else in this process. So if we were to start to focus upon trying to find a match which a lot of scientific questions are focused on. It's a good thing that the small rocky planets are more numerous than the gas giants, but we got to shift our focus because we can't see them as well because they're so small.
Yeah.
And does not see them so well introduce error in our measurement of those smaller. So basically, we have a more difficult task, even though there are more smaller planets that are rock hard.
Yes.
We have trouble with the statistics because we can't get the information back as readily. Is that a reasonable summary?
It is a reasonable summary. You're correct that a smaller signal is harder to characterize. It doesn't mean you can't characterize it. It often means you have to spend additional resources to characterize it, which is why, for example, James Webb was designed to be so large, to be larger than the nose cone of a rocket, and to be able to unfold in space, because it is possible to characterize Earth-like planets. It just requires a lot more resources. You have to gather much more light or gather it for longer. But your point, the underlying point, if I'm hearing properly, is how do you really know, right? And like, especially given the complexity of the problem and the number of Earth-sized planets. And I'll point out like one particular thing, which is, well, we know that there's rocky planets, which are Earth-size, and then there's gas giant planets, which start at Neptune size, right? In our own solar system, which is four times Earth size. So when do things stop being rocky and start being Neptune-like, right? So like in that experiment, so if we picked something, for example, if we needed to go somewhere and we picked something that was 2 Earths across, what's the likelihood that it would be rocky, right? And what we've established, and here it takes measurements of hundreds of objects and statistical arguments, because like any process in nature, there's a lot of variation, right? But what we can identify is patterns. And it seems like if you take something which is 1.5 Earths across, it becomes less likely, 50% less likely that such a world is rocky. So even mapping that margin of what is the nature, is it rocky or is it not rocky? It is answerable. It just requires either more resources or you need to find more of them. That does make the question harder, but it doesn't make it impossible. I mean, it brings up a whole separate issue, which is around the usage of taxpayer money to fund, right? Like, is it worthwhile? So if I told you for $100 million, I could characterize 10 worlds and confirm that they're similar to Earth, right? If you gave me $1 million, I could just tell you that they're not like Jupiter, right? So there is a question with the types of scientific things which are possible to answer and the resources that we put into figuring out the answers. And you're correctly identifying that harder problems require more. I don't know a way around that yet.
One quick follow-up. Life is not possible on a gas giant. Is that true or false?
I don't know the answer. I imagine that it would have trouble evolving there. Yeah. Because I've made this argument that in order to make the basic building blocks of life, there needs to be, I've argued, a murky puddle, a quote unquote murky puddle. The reason why I said that is because you need a situation where molecules are bumping into one another and doing so often enough that this experiment would be repeated over and over and over. How many times can you bump proteins together to make an amino acid, right? And like that particular argument, you need to bump things together so a solid won't do. Right? Like ice is much more difficult. Molecules aren't moving in solids. So to do that experiment where you're bumping things together, neither does it really work in gas because gas is just much more diffuse. So those collisions would happen much less often. It's really liquid where the sweet spot is to have like lots of molecules. And presumably when I say murky, I mean like building blocks of life, gunk, right? Like, so things with carbon atoms in them that are bumping together. I have a hard time imagining how those building blocks would get developed over billions of years in a gas. But that doesn't mean that life which originated in a murky puddle couldn't then ultimately evolve to float. That's my thinking there.
Thank you.
Okay, thank you. John, I think you get the last question.
Okay,
Thank you.
yes. One of the counterintuitive things about stars is that small stars live longer than big stars.
Yeah, right.
And so if it's possible to have a smaller star that would support a planet that would support our kind of life, it would have to be closer in because it's less luminous.
Yes.
But my assumption is that they would have a better chance of being more intelligent because they would have had more time to develop.
Yeah.
Is that a sensible deduction?
So I follow the chain of reasoning perfectly. So there's a major unanswered question, which is, does intelligence actually lend itself to longevity? So we're linking those things as though, like, given an indefinite amount of time, intelligent creatures would evolve and then last. And I think we're running that experiment in real time, on planet Earth. If it were the case that intelligence was associated with longevity, right? So that the longer you had, intelligent life would evolve eventually. So that imagines that intelligent life is evolutionarily favorable. And it certainly seems like evolution is trying it in more than one way, like with dolphins, for example, with human beings, with parrots even, and with octopi. So clearly there is a benefit to creatures trying out intelligence as a strategy. So then given billions of years, it stands to reason in my mind too that intelligence would get tried, right? A number of times, and there would be more time to try it out. What I don't know is, does that mean that you would last longer? And I don't know the answer to that. It could be also in billions of years that you actually would have multiple opportunities to evolve life from scratch. So even if you evolve intelligent life, and unfortunately the story of intelligent life is that we ultimately destroy ourselves. So like imagine this, like
There is always that, yes.
then you would start over, and given another 10 billion years, maybe the story would repeat, right? And on an M dwarf, because they last, as you say, much longer than sun-like stars, there's never a single small star that's ever died, right, in the history of the universe yet, then you could potentially have cycles, right, where you would evolve life multiple times. And to think about that, we're hampered not by the ages of M dwarfs, but by the age of the Milky Way, or not the age of the Milky Way, pardon, the age of the universe itself. Yeah, the age of the universe itself.
Yeah.
So like we can't look at timescales longer than 20 billion years, for example, and ask that question because we haven't had 20 billion years yet. But your point is really well taken. I think about it too.
Okay, when you get the answer, why, let Paula know.
Yeah.
Okay, I will.
Yeah, we would definitely love to have you back. And with that, I'm going to say thank you so much for your time here today. That was a really great lecture.
Thank you.
I certainly enjoyed it. I think everyone else did too. So best of luck with your work. And thank you again for spending time with us today. Very much appreciate it.
Thank you
And
for that.
Very good show.
yeah, and everybody, we've got one more talk next week before the course ends from Bill Gattel, who's going to talk on the transformation of space market and industry. So tune in for one more lecture, and that'll be a wrap for us. So thank you all.
Thank you for having me.
And thank you again, Dr. Ballard.
Yeah, thank you.